Hello, my name is Craig Resnick. I'm coming to you from the ARC Advisory Group. With me today, I have two special guests, Dr. Oliver Brunke, Product Management Team Leader, and Dr. Holger Roth, Senior Training Manager, and they're both from Waygate Technologies, which is a Baker Hughes business. Today, we're going to talk about industrial X-ray and computed tomography solutions. So my first question to you both is, what are industrial X-ray and computed tomography solutions?
Okay, let me start with a little bit background information on NDT, non-destructive testing. So, which are methods which can be used to analyze, visualize, tear apart a component, a piece, a part without actually tearing it apart, without destroying it. So, and there are different modalities for NDT. These days, typically what is used in NDT is ultrasound or borescopes or eddy current or X-ray. And in X-ray, you basically have two different ways to use X-ray technology. Today, one is stationary, where you have an X-ray source and a X-ray detector inside some kind of a system. That's one possible solution, and the other would be portable, where you bring your X-ray source, your detector, to the object in a field, for instance, a construction site or an oil pipeline. Holger, do you want to add anything to that?
Yes, I have to add something because, this is the machine, but to make it a solution, this then my part and the part of my colleagues, which is the application team, you need the application technique to apply this apparatus, this system of hardware components to the respective solution, which includes all the parameters like the X-ray voltage and all these things we maybe talk about later. And to give more or less a recipe or a way of using it to fulfill the inspection task the customer has, which can have a wide variety, which we maybe will speak later about. So the ratio, the relation is something like you have an oven or a stove, and you have the recipe, and then you educate the cook, something like that.
That's very, very interesting. What are some of the main industries where industrial X-ray and computed tomography is applied?
So when we talk about industries, or sometimes we refer to industry as so-called verticals, we speak about typically 5 to 7 industries where X-ray and industrial X-ray and CT is applied. There are big 3, I would call them, where we sell and use our equipment. The first one is aviation, aerospace, and space industry. So everything which is flying, either in the atmosphere or sometimes even outside the atmosphere, and where you need a high reliability of the components, because when something fails in the air and space, you cannot repair it. It's really, really difficult situation then, and then you want to make sure that your quality is at the topmost level. And here we use a lot of the time our technology to ensure that. The other is next to it is automotive, where the requirements are a little bit different. But even more so, the technology is applied in a very broad way to ensure mainly quality and productivity in the industry. The last of the big 3 is electronics, and here we talk about mainly the manufacturing of printed circuit board and semiconductors. But also in recent 5-6 years, we had a lot of application in complete assembly controls of, for instance, smartphones or wearables. So that are the top 3s. And then we can add a couple of other interesting areas. One would be everything around additive manufacturing, here specifically printed metals. Then we have a very important area for our technology, which is the research and development in many of the industries I just already mentioned, but also in fundamental research, in which is many times publicly funded by governments or research associations. Here we talk about biology, material science, or geology. And then we have areas in power gen and medical device industries, which becomes more and more important, because the medical device industry is in a segment which is highly regulated and also requires a lot of attention for quality control and has a lot of complexity. Holger?
Yes, I may add that maybe we do not inspect so much the end product. So you shouldn't imagine that we X-ray cars or airplanes. This may also happen, but not to that extent. It's more or less recurring applications across all these industry. On the one hand, like foundry, you have foundry parts like aluminum cast in automotive, aviation, and medical for sure, or batteries in automotive, as you know today, and electronics, and even in medical devices, you have electronics because many of batteries because they are portable. So this is the one side. You have a lot of different, some different applications which are present in all these industries, but what is the main difference are the requirements. So you have different requirements to testing batteries in automotive than in medical, for example, or for foundry, same. So in automotive, it may be different to aviation. This is the one side. And there are other applications which are very specific for the individual industries. For example, aviation, a typical application would be the turbine blades from the engine. And this is only in aviation. So here we would have very specific solutions for this, so including systems and techniques. Or, for example, in the automotive, where they have certain sensors and so on, which would be rather more specific thing there. So this is the one part of the industry, but also an interesting field is the academia, as we call it. So this is research. And there they have almost every time very unique things. You won't find a second time in your life, maybe, or 3 times. I give just one example. It's the fossils in paleontology. So these scientists have very specific requirements because the size of these fossils varies from dinosaurs to microbes. And so this is always very specific. So there is a very big, say, variety, but some are also recurring throughout all these industries. So this is the reason why you can make specific full solutions for that.
You know, you discussed certainly a broad range of industries, you know, from industrial through research. If we wanted to talk about some of the main challenges, and obviously we can't cover every industry, but let's pick on automotive and let's contrast that to research. What are some of the main challenges, let's say, between using this technology in automotive versus using this technology in research?
Okay, let me start with automotive. So here, obviously, we have a huge market, right? So something like 100 million cars are manufactured every year, and in that order of magnitude, you can easily calculate how many components are manufactured every year for a car. And there are significant number of components which, at least in the design phase, but some even during manufacturing, are inspected using X-ray systems in statistical process control, or sometimes even 100% if it's a really safety critical part, like for instance a suspension part of a car. So and these requirements of a lot of components which have to be manufactured and then potentially inspected require a very short cycle time. So for this inspection, we need to be fast. We need to scan, inspect, and take a decision within, let's say, less than a minute, because of thousands of these parts are manufactured every day. On the other hand, if you're in a mass manufacturing and on the one hand, on the other hand, in a cost-cautious environment, the system need to operate all the time, reliable. So we have reliability, and that brings me to the next portion: mass production reliability. We want to and productivity. That means these, in ideal cases, these systems should run fully automatically. So the part needs to be put into the system using robots or other automation devices. The scan needs to be executed automatically, and also the processing and dispositioning needs to be created in an automated way. So this requires, therefore, very sophisticated, reliable technology, which then ensure that the users, like the automotive OEMs or their suppliers, have a repeatable and reliable solution where we have a higher probability of detection, because we need to make sure that when a part is test it with our equipment, we have to have a higher probability of detection, that we do not see any slip, so that parts who are actually not okay being detected as an okay part. So that would be typical requirements for automotive application.
So, since you have chosen the rough world of cycle times, I will have the pleasure to talk about the opposite, a world where this is not so in the foreground. In research, or say in academics, where you investigate some materials, or as I said before, fossils or soil, just for the sake of to get more information about these samples, the cycle time is not so important quite often. Sometimes even they say, look, for us the time is not really important. We can run it overnight. What we need is versatility, highest performance. And what does highest performance mean? Very high resolution and detail detection. And so what they always also want to do, if they use this method as a subject of research, so they want to develop it or make it more useful for their field of research, they would also require to adjust and change any parameter which is in the system. So this is very important to them. So the software has to enable that. So while in the industry, they want to have it more or less automated if possible, they might want to have it really versatile, and they should be able to influence each of the parameters. And another important difference may be that all these investigations at this time, there are no standards about it. It's not standardized. Like for other things, you have a lot of ASTM, ISO standards, how to do that, and what should be the requirements in resolution and so on. And they more or less can do what they want. So it's a totally different world.
Okay. One thing that I'm sure a lot of our listeners would like to know is, most people are familiar with medical computed tomography or medical CT. What's the operation principle of industrial X-ray computed tomography compared to medical computed tomography?
Let me maybe start with an introduction on the commonalities of both systems. So both systems obviously need an X-ray source, which deliver the necessary source of photons or lights, which need to penetrate the part. Then on the other side, you need to have a detecting device, a sensor. In many cases today, you use some kind of array detector, so like a flat panel detector or something to that extent, which converts the X-rays into, at the end of the day, electrical signal, which then can be converted into a radiograph and then finally into a CT data set. So that is, say, similar. Yeah? And you also need some computational power and algorithms to process the data and create readable 2D or X-ray or CT data. On the differences, we need to look at the CT from a patient perspective. So when you go to a doctor's office or a hospital and need to be scanned, an exam should be short, and you also, because it's not really something which is pleasant, a CT scan, and the dose should be minimized because you do not want to get affected by X-rays. That's very important. So short scanning and minimized dose are key parameters for medical CT. And then you of course need sufficient image quality for the doctors to read the data and to get the right exam out of this. So that is a fine balance you need to find between the cycle time or scanning time and what you actually want to get out of that. So and the patient is in the center of this application. And of course you have in medical CT mainly one application, which is scanning human beings. So everything is dedicated to this. The system is not versatile. It's optimized for scanning you and me. Also, the resolution is optimized for that medical application. And in many cases, I should say, except for maybe medical research, everything is standardized so that it can be run by by staff of hospitals, which have to mainly treat patients and do not have to worry about so much running the CT scanner. So also the inspection parameters are standardized a lot. Where in this industrial, the world is totally different. And Holger maybe can talk about that a little bit.
Yes, I would say from the application point of view, the main advantage of industrial samples normally is that they're very static. They are rigid. You can take them at one end and they don't bow, they do not move, they do not breathe, they have no heartbeat. So because they are dead. So you put them into your machine and you can do what you want. You can move them with some precautions in any direction, on any path. So this is one main advantage. And for that reason, you have a totally different time scale. In medical X-ray, it's almost something like a second. So between the heartbeats, so between the breath and so on. So this is one thing which is very different. And our samples are not or almost not sensitive to radiation. There are some exceptions, like some ceramics which maybe die, or some electronics which may be erased, but this is really the exception. Normally also we do not have to take care about the dose, so we can afford long scans. And why is this important? If you want to have a high resolution, you need special tubes which don't have so much intensity. So you have to make the scans longer to have a higher image quality. And then for that reason, and another thing is what is really different, as Oliver said, they have always one sample in medicine. It's water and bones, so to speak. We have everything between plastics and lead. So quite often we need much higher X-ray energy. And this also affects then the detector. So these detectors have to be hardened against this energy again. So this, you see, this variety also requires a more specific hardware. And you need customized application techniques. As Oliver said before, in medical, you know, this is a thorax, this is the leg, and they do always more or less the same, maybe depending on the weight of the patient. Here we have to customize the application techniques to each of the samples individually. There can be a large variety in batteries or sensors or cast or motor elements. And another thing maybe is the industrial environment. So in the hospital, okay, it's also not easy. Sometimes it may be a little wet there or so. But in industry, you have all possible surroundings. You have foundries, which are dusty and dirty. You have electronics where you have clean rooms. You have more hot areas. You have temperature stabilized areas. So these are the main differences, I think, we have to face when we go from medical to industrial.
Now, you talked a lot about the differences between medical and industrial. When you get into some of the specific industrial applications, are there other differences that apply to the systems?
Yes, definitely. So Holger already explained in detail what variety of applications we have, and due to that fact, we also need to adjust the configuration of our solution according to that needs. So, and mainly 4 or 5 factors may be influencing this. And they are all around what we call the imaging chain and the respective manipulator system. When we talk about the imaging chain, we have on the one side, as I said initially, the X-ray source. And here we typically talk about 2 types of sources, one with high energy for penetrating a lot of material and also high density. So that's the energy we need, and a little bit related to this is also the tube power. So the more power we have, it's like a little bit, the analogy is like the current in fluid mechanics. So when we have more power, more current, then we have a better intensity, higher intensity in the X-ray beam, and that gives us a better signal. So this is the X-ray source side. The downside of having high power is that with high power, we have to go to what we call a higher or larger focal spot size, which is due to the fact that the that we have certain physical limitations of how much power density we can bring on a certain area. And that means if we don't want to melt certain components in the, and literally melt in the X-ray source, we need to limit this power density, and that is then driving the so-called focal spot size. And the focal spot size we need to get small, to get high resolution, on the one hand, but then we have limited power. So this is the X-ray imaging chain we are talking about on the source side. On the detector side, we mainly talk about the so-called detector resolution. So how small is my pixel? And that drives, as a big driving factor of the overall imaging resolution. Can I get to, for instance, 10 micrometer resolution, or is it rather 50 or 100? And the combination of the tube and the detector drive the resolution, and the application then determine which of these components I take. Last aspect of this is what we call the manipulator, so the mechanical device, which is used to allow my CT scanning or my the application or or is driving my part to the position I need it. In a CT scan, in the most simple way, the part is just rotated. But is it rotated accurate enough? Is it long-term stable? These are all factors which determine what accuracy I need, accuracy I need, and based on the application-specific requirements, we pick certain components and therefore have a pretty large variety of different configurations.
Yes, this is all true, and moreover, we talked before about the variety. So this is more or less the toolbox of all things we can use in terms of hardware, software, and system performance. And many things we can calculate. So you have formula and models to find out if you have a certain sample and you have a certain task and need a certain type of image or volume or information out of this data. What is the way to do that? So what do you need to adjust? What tube you choose, what detector you choose, and how to fit all this together. But there's always a part which we do not exactly know, so that we can just put it into an equation or into a model. This is the sample itself. Quite often we do not know exactly how it behaves in the beam or in the system, in the X-ray image. And there is the exact requirements of the users. So they can write down something, but only if you see the results, it can be decided whether this fulfills the requirements or not. And for that reason, we need to do some practical tests. And this is a big effort this company does. We have about 50 application engineers, people who operate the systems and optimize them in about 7 CSCs, Customer Solution Center, as we call it, where we keep many systems covering the whole portfolio to try this out and optimize this before the purchase takes place. So the customer can be sure that we can, elaborate an optimized solution for his or her inspection task. So this is maybe a little different to the medical, as we said before. You wouldn't expect that 50 people first try out what to do with you. So, but here it's different because the variety of applications is so big.
You know, that was a great explanation of certainly the technology and the industries, but can you tell me, let's say, outline 3 of your leading products and maybe explain where some of those products are applied?
Sure. So maybe we picked some of the typical applications in the portfolio. We have 10 plus solutions, as you can imagine from the explanation, to address a different need. And we picked 3 specifically. One is what we call SpeedScan CT64, which is actually, and that's the interesting piece, based on an imaging chain which is taken from a medical CT scanner. So what we did actually here is we figured out that this for this a certain application, and this is mainly in light metal castings, complex castings, which are used in combustion engines, but also in castings for electric vehicles. That the resolution and power which is used in a medical scanner fits very well to this application, and we learned this few years back, 5-6 years back, and now it is successfully applied in a lot of foundries around the globe. So that would be a high-speed CT scanner. That's why maybe speed scan CT64 is not the worst name. And it is used for production process control in foundries. The other example I'd like to pick is our latest generation of 2D and CT scanning system for the electronic industry, for inspection or high resolution inspection of printed circuit board solder joints, as well as semiconductor features, which is called the Nanomex Neo. That's really a high-end, very high resolution. We can go to less than a micrometer resolution and 200 nanometers of detail detectability, and was launched mid of last year. And that's maybe two highlights out of the portfolio. And I think Holger wants to mention a third one.
Yes, my favorite one for sure, which I think is my favorite one, is our Vitomex M metrology, which is volume tomography systems, which not only gives real excellent image quality because it has the latest detectors and 300 kilovolt tube, which is very rare on the market, I would say. It is able to do dimensional measurements in industry. So maybe you can imagine there are measurement tools in industry where you measure lengths, diameters, and so on in workpieces or technical devices. And this is what this system does to a high degree of accuracy, something like in the range of 5 microns or so, just to give you an idea. And this is applied to also, again, a large variety across the above mentioned industries like medical devices. So medical devices normally have a higher requirement to precision and accuracy in manufacturing. And connectors in automotive. You wouldn't, maybe if you're not in this field, you wouldn't imagine how complicated these connectors in automotive or especially in cars are. So, and they're produced in a mass production, but still they have to be fit very accurate into each other to ensure the electric conductivity throughout the whole network in the car. And this is really an important task to do, because I think it's still like this, that 50% of defects of cars are of these electrical connectors and the cables. So here, this is important. Or if you look at these aircraft blades and so on, you would also measure the geometry to repair them or to replace them and so on. And same holds for defense, where they also have high reliability products, which are quite often too difficult to measure. And so this would be an application. You might ask, why can't you do it in another way? X-ray goes through the samples, and so you can also measure inside or behind obstacles where you cannot access by the usual tactile or optical means. And so this is now a real field of development and an increasing market. And this system is really a feat of precision, and is the reason why I like it so much.
Yeah, I mean, you brought up metrology. What's different in such a metrology system?
You know, typically in such an X-ray system for these industrial things, we use a certain degree of magnification in the image, so that the object is not imaged 1-to-1, but with a certain magnification. And the resulting data we call the volume, which shows the object, so to speak. And this consists of data points, and they have a certain size, or you could say distance. And if you want to measure, you need to know exactly how big these data points are, or what is their distance exactly, because this is the scale on which you measure. You must imagine it's something like 80.753 something microns. So we need to know this, I would say, up to 5 digits. And now this is not so easy to manage as one might think. For this, we would need to know exactly the magnification of the system, which is a property of the geometry. And so we had to develop special means and techniques to determine this geometry of the system so that we know it to 5 digits. This is point number 1. And then you have to keep this geometry stable over time. So this system needs to have the same temperature to compensate for the heat extension. And it has to have also a mechanical stability. So, for example, these manipulators in such systems are made of granite, so which is a very rigid stone. And this is not everything. Still, the X-ray images or the tomogram is the base of these measurements, because in this tomogram we look for the surfaces with certain mathematical methods, and therefore this image has to be as perfect as possible. And naturally, these by some very elementary physical reasons, these CT images are affected by image artifacts, so things which do not really exist, but which are caused by the method, so to speak. And so you have to correct for these artifacts. And here we made some real, I think, impressive progress, so that we could improve the accuracy even more, so that I think it's now among the leading systems on the marketplace.
No, that's really interesting. And as a final question, and to kind of elaborate on that, can you provide some examples of technology highlights that you've recently launched, and how have customers benefited from it?
Yes, just concerning this correction of artifacts or improving of image quality, we just launched, not long ago, 2 detectors, which have a very, very high sensitivity and a very good resolution. So just to give you an idea, one has a pixel size of 100, the other one of 200. So maybe this does not tell you much, but with this variation, you can cover a very wide range of applications, since it's not such simple that the smaller pixel gives you just a better resolution, so it's the better detector. You have other properties of detector, like, for example, the signal to noise ratio or contrast to noise ratio, as you may call it. And so together, these 2 detectors now cover a really wide range of applications. But in the full range, they improve the image quality such by the higher sensitivity, so that we could now create X-ray images of much better quality. And if I now go back to this metrology system, of higher accuracy too.
Yeah, and Holger, just a slight addition to your comments. I think you forgot the unit. I mean, the pixel size is 100 and 200 micrometers.
Again,
and I would like to add maybe a little bit, as a closing comment to complement or add to technology we have launched recently. Some tools we have developed, software mainly, but not only, to overcome of these artifacts you mentioned about. As you said, artifacts in imaging are features which are caused by the method and not truly part of the component you're scanning. And that's why you don't want them in the data set, because your operator or your software analysis tool might be confused by this. So, and that's why we put a lot of effort in artifact reduction. And one very, in the industry, almost famous example is our scatter correct technology. And we are pretty proud about this, because we kind of, I think, started a significant discussion about this a few years back in the industry. And scatter correct essentially does something which is pretty cool, because we are not just applying mathematical methods to simulate the artifacts and then try to eliminate it. We have found a way to measure artifacts caused by scattering, but by indirectly being able to measure scattered radiation. In simple words, X-ray are not just on a straight line penetrating your path. Some of the X-rays are scattered, and this scatter signal is contributing in a way that it creates unwanted features, artifacts. And if you can measure the scatter contribution in the image, you can basically reduce this kind of signal from your image and eliminate to a large scale this kind of artifacts, and therefore be able to get much cleaner images in a very effective way. And that allows us, in coming back to the benefits, to measure in a very effective way parts which in the past could only be measured with a different X-ray method in a much longer slice by slice manner. So in that way we can increase the effectiveness of X-ray technology, especially in manufacturing, easily by a factor of 10, or sometimes even by a factor of 100. So the benefit of this artifact reduction technology, which is maybe can be pretty complicated if you think about that, but the benefit is very straightforward. It's a higher productivity and faster scanning, and that's something which is always in the heart of what we do when we try to invent new tools. We try to think about what's the benefit for the customer of it, in order to make our systems more attractive for our customers.
Well, it sounds like you got certainly a great portfolio of solutions that are going to certainly meet or exceed the needs of your customers. That was a great overview of industrial X-ray and computed tomography solutions. So please join me in thanking Dr. Oliver Brunke, Product Management Team Leader, and Dr. Holger Roth, Senior Training Manager from Waygate Technologies, a Baker Hughes Business. This is Craig Resnick coming to you from the ARC Advisory Group. Thank you so much. Have a great day.